In this video, I'm going to show you how to simulate a Bose-Einstein condensate in 2 dimension using the damped gross Pitaevskii equation, and using ComFiT, of course. And so here I've installed ComFiT, and the plan for this video is that first we're going to initiate a distorted, not boundary condition, but initial condition. And then we're going to relax the Bose-Einstein condensate, and then we're going to have a look at the vortices that are created when you do that, and then we're going to create an animation of these vortices. So I'm going to import the packages that I will need. I might need more as we go on. I don't quite remember. So this is called the damped gross Pitaevskii equation, and it's essentially a way to model a Bose-Einstein condensate using a sort of macroscopic wave function. So this psi here is a complex field, and it evolves according to this equation, which is called the damped gross Pitaevskii equation. And there's a lot of literature that you can look up if you're interested in that, or you can go to confitlib.com, where we've also written a bit about it. But in short, the gross Pitaevskii equation is the one where this gamma variable here is set to 0. So then you get the gross Pitaevskii equation. And if gamma is non-zero, then it's called a damped gross Pitaevskii equation. Essentially, it means that some of the energy is dissipated, so that the Bose-Einstein condensate will go to its sort of ground state. This is just going to be a quick video where I show you how to start using it, not go too much into the theory. But let's just start by setting up our system. So I'm going to create an instance of the Bose-Einstein condensate class, which I'm going to call BEC, and it's going to be a 2-dimensional system. So cf.bose Einstein condensate, and the dimension is going to be 2. And for the limits, I don't know, let's just use -1 to, or actually -50 to 50, and then the same with the y limits. Doesn't really matter. By default, it's 0 to 100, but let's just use this now just to see that you can do something like this. Okay, so that creates my instance of the Bose-Einstein condensate, and now I need to set an initial condition, which I can do by, and the initial condition that I'm going to have is an initial condition which is 0 everywhere with some random noise, just to get to break some symmetry and get some stuff going. Because if I just set the initial condition to be 0 everywhere, then nothing's going to happen, because it's sort of perfectly 0, and so the right hand side is going to be 0, and then everything's going to be 0. So I need some small variations. So I'm going to set BEC that psi is equal to, and then I'm going to create a random initial condition. So np.random.rand. And then the dimensions here, I'm just going to use the dimensions of the systems, which is contained in bec.dims. So bec.dims is a variable that just lists the dimensions of the system, which is perfect for inserting into rand. Now this is going to create a number which is between 0 and 1, and typically I don't want that. I want something between something that's symmetric around 0, so I'm going to subtract 0.5. So this is going to create a number which is between -0.5 and 0.5. I suppose I can just show you that. So something is wrong. List object cannot be interpreted as an integer. Oh yeah, right, because I think I need okay, maybe I need to specify xres and bc.ys. Is that how it works? Okay, it seems to work. Let's just print to see if it's happy with that. Okay, that looks about right. So let me just show you how this looks. So if I do bec.plotField bec.psi, then you can see that it's essentially a random field between minus 0.5 and 0.5. Now, this is typically too much of a variation. So typically I'm going to scale this by like 100th, for instance. So if I do that, I get the same type of random field, except now it sort of varies between minus 0.05 and 0.005. Okay, but this is a real field, and this psi field here should really be a complex field when we're working with a Bose-Einstein condensate. So in order to get a complex field, I'm simply just going to add on a complex part of this, the same as a random complex part of this as well. Now, I think if I run this function here, just plot field, as if it were a real field, I think it's going to give me a warning that the provided field was complex, and it suggests that it might be a residual part from the Fourier transform. It is not in this case. It's actually a complex contribution, and here you can see the max imaginary part. So it's just plotting the real field in this case. So in order to see the complex field in all its glory, then we just write plot complex field instead. And here you can sort of see the complex field. And the way that complex fields are plotted in ComFiT is by showing you the magnitude as the... so a complex number has a magnitude and a phase, and the phase is plotted with this color bar, and the magnitude is the intensity of the color. So where the function is white, it means that it's closer to 0, and where it says full color, that's where it's closer to the maximal value, and the color here is showing you the phase of the field. So as you can see, it's a random complex field. Now, in order to produce something, yeah, and I can also show you, if I plot the absolute value of this field, then you can see that it's quite small. So you see here, here's the absolute value of this complex field. It's quite small everywhere, 0.007. Now, in order to get a if this was interpreted as a Bose-Einstein condensate, it would be a disordered state, which was not sort of in the Bose-Einstein condensate phase of the system. So in order to get it to be that, we need to allow it to relax according to the this equation. And the way that that's done is essentially just by removing this I part of the equation and setting gamma equal to 1. That's essentially going to make the sort of magnitude of the wave function go towards its equilibrium value. Again, there's a lot of math and theory behind this, and you can look it up if you want to, or go to confitlib.com. But for now, I'm just going to make that relax. First, I need to add the Fourier transform of the field to the instance as well, because that's going to be needed to evolve it. Now, in order to evolve it according to gamma equal to 1 and not ignoring this I part here, then I'm going to write BEC.evolve relax BEC. So that's what it's doing. And then I need to specify the number of time steps. So let's just say 100, for instance. And then afterwards I can, okay, now it's done that. So now I can plot the, let's plot the complex field now. So if I do BEC.plot complex field BEC.psi, you can see that now it's sort of formed this more orderly state. It's not random anymore. Like we cannot see the magnitude here. So if I want to see the magnitude, I instead want to plot the magnitude of this field, BEC.psi. And you can see that the magnitude has now approached 1, which is the equilibrium value of the field, except for these points here that are, which are what we call vortices in a Bose-Einstein condensate. So a Bose-Einstein condensate contains vortices, and these are shown as zeros of this complex function here. So if I continue to evolve it a little bit before plotting, essentially what's going to happen is that as you are relaxing the Bose-Einstein condensate, these vortices are going to annihilate against each other. So positive vortices are going to annihilate with negative vortices. And let's just see how that looks. So I'm just going to relax it a little bit more. For, let's say, 100 time steps more, and then I'm going to plot the absolute value again. Then you can see that these vortices have become more defined because some of these have annihilated against each other. And the reason that we call them vortices is that, so here I'm just showing you the magnitude of the complex field, but if I plot the complex field itself, so BEC.plot complex field BEC.psi, you can see that around these points where the magnitude goes to 0, so for instance, let's pick this point here at -20, -45 here, you can see that it has this, the complex phase of the wave function is increasing from 0 to pi/3 to pi and then back again around 0. So it sort of evolves towards this it has the circulation of 2 pi around this point, which is why we would call this a positive integer, so a +1 vortex in terms of the Bose-Einstein condensate. And as I'm continuing to relax this Bose-Einstein condensate, these vortices are going to evolve. Now, for the complete Bose-Einstein, for the complete evolution of damped Gross-Pitaevskii equation, then we both have this I term here, which is responsible for the sort of the turbulence of the Bose-Einstein condensate, and then this gamma is the part that has to do with the dissipation of energy in the Bose-Einstein condensate. So if I don't remember what is the default value of gamma in when you just initialize like this, we can check. So yes, so the default value of gamma is 0.01, meaning that if I just evolve the equation according to the damped Gross-Pitaevskii equation, it is going to dissipate a little bit of energy, meaning that these vortices are going to annihilate against each other, but they're also going to move around a lot. So if, for instance, if I evolve the Gross-Pitaevskii equation for a little bit, so evolve damped Gross-Pitaevskii equation for, let's say, 10 time steps, and then afterwards I'm going to plot complex field BEC.psi, then these vortices that you see in this figure here are going to move a little bit. So you can see, maybe it's kind of hard to see, but these vortices have sort of moved a little bit. Of course, it's hard to see. It's hard to see in this sort of picture by picture. So in order to get a better view, I'm going to leave this phase plot aside, and I'm going to focus on just looking at the magnitude of the Bose-Einstein condensate, and I'm going to create an animation showing how this magnitude field evolves and how these vortices in the Bose-Einstein condensate moves with respect to each other. So how do we do that? Okay, so we're going to create a for loop. So let's use 100 time steps, 100 images in our loop. And then for each step in our loop, we are going to evolve the Gross-Pitaevskii equation for 100 time steps, depends on how fast we want it to move. Let's do 100. And then we are going to make a plot. I might need matplotlib. And so we're going to make a plot of this function. So we're going to do BEC.plot field, and then we're going to plot the absolute value of BEC.psi. And then to create an animation, I'm going to need to save the plot, and that I have a function called tool save plot, which is just going to save an image of the field at this position at this time. And just to know where we are at, I'm also going to print n while we're running it. And then after the simulation has done all of these things, then I'm going to create an animation GIF. And this needs n as an argument. And I think that is it. I hope that it's going to write over the files. Oh, it looks like I might not need this actually. Okay, so let's see how it goes. Okay, so it's running, so it's creating images 1, 2, 3, etc. Now these images are actually being saved in Colab here, so you can see they are here. So let's say if I download this one, then I get this plot here. So you can see that the field is sort of moving, changing with time. And if I go to some later time, now we're at 34. So at some later time, it has changed still. And it has some of these. There are fewer vortices now, so some of them have annihilated against each other. Now, one thing to keep in mind here is that I forgot, in making this plot, I forgot to set the limits on the color bar, which means that actually this color bar is going to be continuously adjusting itself in the animation. But if you wanted to fix the color bar so that it looks better, you could do that by setting the VLIM properties to 0.1, for instance. That would fix the color bar so it doesn't go up and down. But that is something you can do if you want. I think we're closing in on the finishing line now. Let's have a look at some of the later plots. It needs some time to update, I think. Image number 89. How do you look? Yes, you can see now there are not many vortices left. And so now it is creating, it's done with the last plot, and it has created this animation, which is called, it's called the date of making it and the time, and then a name. And you can specify the name as well if you want in this here. But let's just look at the animation as it came out. So here you can see how the Bose-Einstein vortices in the Bose-Einstein condensates are moving. And so if this was purely dissipative, you would not see this sort of turbulent behavior. So if you were to just like do the relax thing, then the vortices would just move towards each other and annihilate. But since it has it's evolving according to the Gross-Pitaevskii equation with the I term, the vortices are also moving around according to the Gross-Pitaevskii equation. And you see that the positive and negative vortices are annihilating against each other. So I recommend having a look, trying it out, and have some fun.